Welcome to my class. Let's look at matrices. So I'll begin by defining what a matrix is and say that a matrix is a rectangular array of numbers or objects. Is a rectangular array of numbers or objects. Array of numbers or objects. Now, for instance, we can represent a matrix as, matrix A as A1, 1, A1, 2, A1, 3, all the way up to A1n. So this is the first row. The second row we will have A21, A22, A23, all the way up to A2n. The third matrix will be that way, the same way. We'll have A31, A32, and so on. This will continue up to the row M. Row M. Row M, so we have AM1, AM2, AM3, all the way up to AMN. So this is how we represent a matrix. Now, what do these numbers mean? The numbers 1, 1, 1, 2. Now, this is a row. This is the first row of matrix. This is the second row of matrix. So the first row of matrix, the first number here represents the row. So that's why you see A1 means this element is in row 1. This element is in row 1, column 2. This one is in row 1. So the second number here represents, so the first number represents the rows, represents the number of the row, represents the row, and the second number represents the column, represents the column. So the rows are the horizontal ones, and the columns are the vertical ones. So this element, for instance, is in row 1, column 1. This one is in row 1, column 2. This one is in row 1, column 3, and so on. Row 1, column n. This element is in row 2, column 1, row 2, column 2, row 2, column 3, and so on. This one is in row M, column 1, row M, column 2, row M, column 3, and so on. So this is how we represent a matrix. By the element is identified by the row in which it is, and then the column in which that element is. For instance, this matrix, let me give you another matrix here. For instance, this matrix B, if I'm given element 2, 3, 1, negative 4, 0, 9, 8, 1, 4, 3. Here, element A1, 2, the element in row 1, column 2, row 1, column 2, this is that element, 1. The element in row 2, column 2, this is row 2, column 2 is this, so that element is 9, and so on. That's how we identify elements in a matrix. Now, so I've said that we give a matrix by first stating the row and then the column. And let's look at this matrix. This is the first row, the second row, the third row. And how many columns? 1, 2, 3. So it has 3 rows and 3 columns, and therefore we say that this is a 3 by 3 matrix. So this is the size of the matrix. The size of the matrix. So we give the size of the matrix by stating the number of rows, and then the number of the columns. For instance, this matrix A, 1, 2, 0, 7. I can see 2 rows and I can see 2 columns. So the size of this matrix is 2 by 2. Now what you notice is that in the 2 matrices I've given the examples here, these 2 matrices, you discover that the number of rows is the same as the number of the columns. For instance, here the rows were 3 and the columns were 3. So this, and here we have 2 rows and 2 columns. So when the number of the rows and the number of the columns are the same, then we say that is a square matrix. Square matrix. So a square matrix is one whose the number of rows and number of columns are equal. Now let's look at another example. Let me write another example. So you now know what a square matrix is, and you know how to give the size of matrix. At the size of matrix, first of all, you'll be giving us the number of the rows and then the number of the columns. Now what is the size of this matrix? What's the size of this matrix A, which is 2, 4, 7, 8? What's the size of this matrix? In other words, how many rows are here and how many columns? I can see 1 row, this, and the columns I can see 1, 2, 3, 4. I can see 4 columns. So the size of this matrix is 1 by 4. How many rows are here? We have only 1 row, and therefore this type of matrix is called a row matrix. A row matrix. So a row matrix is a matrix with only 1 row. We can also have another matrix, B, that is 1, 0, 7. So the size of this matrix, I can see 3 rows, and I can see 1 column. 1, 2, 3 rows, 1 column. So this is the size of this matrix, but it has only 1 column, so we call it a column matrix. Call it a column matrix. Now, so we've talked about square matrix. We also have a matrix C. Matrix C, for instance, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. You can see that this diagonal has 1, 1, and also you have zeros. And so this is the identity matrix. Identity matrix. These are 3 by 3 matrix. The identity matrix for 3 by 3 matrix is this. These are 3 by 3. You can see 3 rows, you can see 3 columns. So this is the identity matrix for 3 by 3 matrix. The identity matrix for 2 by 2 matrix would be 1, 0, 0, 1. So this is the identity matrix for a 2 by 2 matrix. So you can also get identity matrix for 4 by 4 matrix, and so on. Now, so we know what a square matrix is. So the other thing I want us to define is the word diagonal matrix. I want us to define diagonal matrix. So as the name suggests, this matrix will be a matrix with only non-zero elements along the diagonal, and also will have zeros. For instance, if I have this matrix, this is a diagonal matrix. You can see that we have only non-zero along the main diagonal, and elsewhere we have zeros. So these are diagonal matrix for a 2 by 2 matrix. But 3 by 3 matrix would have a diagonal matrix like this: 2, 0, 0, 0, 7, 0, 0, 0, 9. So this is a diagonal matrix, and it's a 3 by 3 matrix. So you need to know what a diagonal matrix is. You need to know what row matrix is, what a column matrix is, what a square matrix is. And the other thing that you need to know that is very important to us is, when do we say that matrices are equal? So two matrices are equal if the corresponding entries are equal. So if the corresponding entries are equal, then we say that, and it must be of the same size and are of same size. So if they're of the same size and the corresponding entries are equal, then we say that the two matrices are equal. For instance, matrix A here, 2, 0, 1, 0, 1, 3, is equal to matrix B here, 2, 0, 1, 0, 1, 3. So these two matrices are equal. You can see they are all 2 by 3 matrices, 2 by 3. Their sizes is 2 by 3, 2 rows and 3 columns, 2 rows and 3 columns. And you can see that the corresponding entries are equal. The corresponding entries are equal. So that's what we say that. That's when we say that two matrices are equal. Now we can do this example. That find x and y if matrix A equals, or let me just say, find x and y if find x and y if 2, 3, 1 x equals to y 3, 1, 4. So find x and y. Now, since these two matrices are equal, it's very easy for us to find. I can see that y equals to 2. I can see that y is equals to 2. Because the two matrices are equal, and we say that two matrices will be equal if their corresponding entries are equal, and they must be of the same size. So we can see the equality sign here. So it means this matrix equals that. So if this matrix equals that, then it means that these two must be equal to 1. 3 is equals to 3, 1 is equals to 1, and x is equals to 4. X is equals to 4. So that is how we say that matrices are equal. Now, these are simple things and we already know them. So just reminding ourselves on some of them. That when do we say that matrices are equal? Now, the other thing that I want us to remind ourselves is, how do we add matrices? Addition of matrices. How do we add matrices? Now, we add matrices by adding the corresponding entries. We add by adding the corresponding entries. We can only add matrices. Matrices can be added only if they are of the same size. If they're of the same size, then you can add. If they're not of the same size, you cannot add those matrices. E.g., if A is 2, 1, 4, 7, and B is -3, 4, 3, 9. Find A plus B. So this is very easy. This is very easy for us. A plus B would just be 2147 plus -3439. And when you do this, you add the corresponding entries. 2 plus -3 gives us -1. 1 plus 4 gives us 5. 4 plus 3 gives us 7. 7 plus 9 gives us 16. So we've added these two matrices. And what you've noticed that these two matrices were of the same size. And so it was easy for us to add them. Now we can also multiply matrices by scalars. We can multiply matrices by scalars, and let's just look at an example. Matrix multiplication by scalars. A scalar is just a number, just a constant. Now, so if A is 2, 4, -1, 3, find 3 multiplied by A. Find 3 multiplied by A. And this is very easy. You can do this. So 3 multiplied by A is just 3 multiplied by 2, 4, -1, 3. And we are multiplying 3 by each of these entries. Multiply 3 by each of these entries. What you get here will be 6. What you get here will be 8. What you get here will be, no, that is not 8. 2 times 3 will be 6. 3 times 4 will be 12. And 3 times -1 will be -3. 3 times 3 will be 9. So this is 3A. Now try this question. If A is 0, 1, 2, 3, 4, 1, and B is 1, 1, 0, 0, 3, 4. This one is 3. Find A plus 2B. Find A plus 2B. Try that. Try that and then compare with my solution here. My solution will be A plus 2B will just be, I have A here, 1, 2, 3. Now 1, 0, 1, 2, 3, 4, 1 plus 2B. 2 into 1, 1, 0. This was 3. This was 3. So this will be 0, 3, 4. So just multiply the 2 by the whole of this, and then add it to this. So when you do that, you get 0 plus 2, which will be 2. You get 1 plus 2, which is, and 6 plus this 4 will be 10. 2 times this 8, no, times this 4 will be 8. 8 plus this one will be 9. That's how we multiply matrices by scalars. Now, I want to remind you how to multiply a matrix by another matrix. Matrix multiplication. Now, to multiply matrices, the columns, the number of columns of the matrix on the left must be equal to the number of rows of the matrix on the right. For instance, if A is, and look at the columns here, 2, 3. These are 2 columns. If A is that, and B is, the rows here are 2, 1, 2. Find AB. So you just ask yourself, how many columns are here? So if the columns are 2, what about the rows here? If the rows are 2, then it means we can multiply this matrix. But if the number of columns here are not equal to the number of rows here, then you cannot multiply those matrices. So these ones can be multiplied. And when we multiply, what will be the solution? 2, 3, 1, 4 multiplied by 1, 1, 2, 1. And so how do we multiply? We multiply this row and this column as we add the results. So for instance, 2 times 1 would be 2. So I'm multiplying this row and this column. 2 times 1 would be 2, and 3 times 2 would be 6. And then I come to this other column using this row. 2 times 2 times 1 would be 2. And 3 times 1 would be 3. Now I'm done using this row and the whole of these columns. Now let me come to this row. 1 times 1 would be 1, and 4 times 2 would be 8. I'm done with this row and this column. Let me come to this row and this other column. 1 times 1 would be 1, and 4 times 1 would be 4. So we multiply as we add the results. And what does this give us? The first element there is 8. The second element there is 5. This other element is 9. And this one is 5. So we multiply this matrix because they were compatible. So they are compatible if the number of columns of the matrix on the left equals the number of rows of the matrix on the right. Then we say that those matrices are compatible. And therefore, we can multiply. Let's look at another example. Another example. Let A be the matrix 1, 2, 3, and B be the matrix. Let me look at the columns here. 1, 2, 3. So I need 3 rows here for the matrix to be, these 2 matrices to be compatible. So I need 3 rows. 1, 0, 2. I can add another column. 1, 2, 4. Find AB. So let's see, is AB compatible? Is A compatible to B? A is on the left. So the columns are 3, the rows are 3. So we can multiply this. 1, 2, 3, multiplied by 1, 0, 2, 1, 2, 4. And when you multiply this element times this element is 1. This element times this element is 1. Plus this element times this element is 0. Plus this element times this element is 6. So I'm done with this row and this column. Now what about this row inside the column? 1 times 1 will be 1. 2 times 2 will be 4. 3 times 4 will be 12. So what does this give us? The first one is 7. And this is 5 plus that, which gives us 17. So you can see we were able to multiply this matrix because the columns on the left were 3 and the rows on the right were also 3. What about, are we able to find B times A? So let's count the columns in B. 1, 2. We have 2 columns. And because B is on the one on the left, what about the one on the right? How many rows? 1. So that means we cannot multiply this. We cannot find BA. Cannot find BA because they are not compatible. The columns on the left are not equal to the rows on the right. So it's not possible to do that. So you notice therefore that for matrices, AB is not necessarily equal to BA. Because, for instance, in this case, we found AB to be this, but BA is not there. BA does not exist. You cannot find it. So they cannot be equal. For matrices, this is not always. It's not always true that AB will be equal to BA. So AB not necessarily equal. It's not always equal to BA. Now, I don't know whether you've noticed something. And if you've not noticed, let me just assist you notice it. If you've not noticed something here, have you noticed that when we found AB, the number of rows were the same as the matrix on the left side. And the number of columns were the same as the matrix on the right side. So that if matrix A is a 2 by 3 matrix and matrix B, this one has how many columns? That so it's a 3 by 4 matrix. Then we can find AB because the columns here are 3 and the rows are 3. But what will be the size? What will be the size of AB? So the columns, the rows will be the same as those in A. So A has 2 rows. And the columns will be the same as those in B. B has 4 columns. So AB would be of size 2 by 4. So you can easily tell, therefore, because you just take the rows here and take the columns here, and that will give us the size of the new matrix. That will be the size of the new matrix. Let me just give an example. If you have 2 columns, 1 by 1, 2 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 by 1 if A is 2, 1, 4, 3, 0, 1, and B is 1, 0, 1, what would be the size? What would be the size of AB? It's easy. It's easy. That the size of AB, I take the rows of A. I take the rows of A, which are 2, 1, 2, and I take the columns of B, which is 1. So I expect that the size of AB would be 2 by 1. Be 2 by 1. So I expect 2 rows and 1 column. Let's see if that is true. Let's see. A is 2, 1, 4, 3, 0, 1. Multiply this by B, which is 1, 0, 1. 2 times 1 is 2. 1 times 0 is 0. And 4 times 1 is 4. We are done with the first row and the only column. So we come to the second row. 3 times 1 will be 3. 0 times 0 will be 0. And 1 times 1 will be 1. So what do we get? This is 6. And this is 4. So this is a 2 by 1 matrix. Actually, it's a column matrix. It's a column matrix. It has 2 rows and 1 column. So that means what we've stated, that if you're given the rows, if you're given the size of A and you're given the size of B, we can easily tell what the size of AB would be. So it will be very easy for us to do that. Good. I want to show you how to get the determinant of a 2 by 2 matrix. Determinant of a 2 by 2 matrix. And later on, I'll show you how to find the determinant of higher order matrices. You learn how to get determinant of a 3 by 3 matrix. And even the inverse, I'll also show you how to get the inverse of a higher order matrix. Now, if A is a matrix A, B, C, D, then the determinant of A denoted as that A will just be the product of this diagonal here, which is AD, minus this other product, the product of this other diagonal, which is BC. So that's how we get a determinant of a 2 by 2 matrix. That you take this diagonal, product of this diagonal, minus the product of this diagonal. E.g., if Q is a matrix 2, 4, 1, 8, then the determinant of Q, which we denote as that Q, will be this product, which is 16, minus this product, which is 4. And that gives you 12. So the determinant of this matrix is 12. Any matrix with that determinant, any matrix with the determinant not equal to 0 has an inverse. Any matrix with the determinant not equal to 0 has an inverse. So that means we can now find inverse of a matrix, of a 2 by 2 matrix. Let's try to find the inverse of a 2 by 2 matrix. Now, if A is 2, 1, 0, 4, or let me even say that A is 2, 1, 3, 4. Find the inverse of A. So this is how we shall be denoting the inverse of A. Find the inverse of A. So our solution, normally, the first thing you do is to find the determinant. So the first thing you do is to find the determinant of A. And the determinant of A is this product, which is 8, minus this product, which is 3, and this is 5. And so the inverse of A would be 1 over determinant times the adjoint of A. Now, for a 2 by 2 matrix, the adjoint, if A is this, just a minute before you come back to the inverse of A, before you come back to that, if A is this, then the adjoint of A, which we shall abbreviate as something of that adjoint. So the adjoint of A, which we shall abbreviate as adj A, shall be the matrix that is formed when you interchange this leading diagonal and change the sign of this other diagonal. So the sign here is positive, so make it minus, and the sign here is positive, make it minus. So that is how we find the adjoint of A. E.g., if A is 1, -3, 4, 7, then the adjoint of A shall be, just reverse this, interchange this, 7, 1, and then interchange the sign here. The sign here is positive, make it negative, and the sign here is negative, make it positive. So that is the adjoint of A. So I've said here, that to get the inverse of this matrix, I'll take 1 over determinant times the adjoint of A. You now know how to get the adjoint of A, and so let's get the inverse of this matrix. Let's get the inverse of this matrix. So we know the determinant here is 5. So the inverse of this matrix is 1 out of 5 times the adjoint of A. The adjoint of A, let's interchange this, 4, 2, and interchange the sign here, -3, -1. So the inverse, you can leave it in this form, or if you want, you can write it as 4 out of 5. Just multiply a fifth inside. 4 out of 5, -1 out of 5, -3 out of 5, and then 2 out of 5. So that is how you get the inverse of a 2 by 2 matrix. So as the exercise, you can try to find the inverse of the following matrix. If it exists, find the inverse of the following matrices. And as I said, I'll show you how to find the inverse of a 3 by 3 matrix, 4 by 4 matrix, and you can generalize that to higher order matrices. I want you to find the inverse of matrix A, which is 7, 2, 0, 4. Matrix B, which is 1, 1, 0, 7. And matrix C, which is 14, 2, 7, 1. Find the inverse if it exists. Now, so that is how we find the inverse of a 2 by 2 matrix, and I've also shown you how to find the determinant of a 2 by 2 matrix. Now, I want to show you something about transpose. Transpose. You need to know what a transpose of a matrix is. I'll use this knowledge of transpose in determining the inverse of a higher order matrix. When I come to showing you how to find the inverse of a 3 by 3 matrix, 4 by 4 matrix, the knowledge of transpose will be very important. That is why I want you to know it now. Now, the transpose, by definition, the definition of this, the transpose of matrix A denoted as A transpose, A with a T, power T here, power T, denoted A transpose. Is the matrix formed when the first row of A is made the first column, the second row of A is made the second column, and so on. Or you can make the first row, the first column of A become the first row, the second column become the second row, and so on. E.g., if A is 1, 2, 3, 4, 7, 9, 6, 0, 7, then what is A transpose? Just make the first row be the first column. 1, 2, 3. The second row make it the second column. 4, 7, 9. 4, 7, 9. And the third row make it the third column. 6, 0, 7. So this is a transpose of A. This is a transpose of A. So this is how you find the transpose of matrix. And as I said, you would have made the first row, the first column with the first row. And you can see that is what is happening here. The first column is the first row. The second column is the second row. The third column is the third row. So that is how we find the transpose of the matrix. And it's very easy to find the transpose of a matrix. Now, let's look at solutions to systems of linear equations. This is what we call simultaneous equations. So I want to see how to solve simultaneous equations, and I want to use matrix method, but later on I'll show you other ways of solving. I'll show you other ways of solving this kind of questions. So use matrix method to solve 2a plus 3b is 7, a plus 4b is 5. We want to solve this. Solution. The first thing you do is to extract the coefficients of a and b. So you want to extract the coefficients. In the first matrix, the coefficient of a is 2 and the coefficient of b is 3. In the second equation, the coefficient of a is 1 and the coefficient of b is 4. Let me call this matrix A, or just leave it the way it is, or let me call it matrix A. Then find the determinant of A. Then find the determinant of A, which is 8 minus 3, that is 5. 8 minus 3, that is 5. We now to do that. We now to find the determinant of the matrix. Then the next thing I'll do is I'll find the inverse of A. I'll find the inverse of A, which is 1 over determinant multiplied by the adjoint of A. So the adjoint of A is 4, 2, negative 1, negative 3, which is just 4 out of 5, negative 3 out of 5, negative 1 out of 5, and 2 out of 5. So this is the inverse of A. So now what is the value? We wanted to solve this. We want to find the value of A and the value of B. So to find the value of A and B, what I do, I write that the value of A and B is equal to this inverse, which is 4 out of 5, negative 3 out of 5, negative 1 out of 5, and 2 out of 5, multiplied by this constant, 7, 5. Multiplied by that constant, 7, 5. So the steps are very simple. I just found the determinant, then found the inverse. And now I say that A, B is, I multiply the inverse here by this constant. So what do you get when you multiply? 4 out of 5 times 7 would be 28 out of 5. And then negative 3 out of 5 times 5 would be negative 3. So I'm done with the first row and this column. I come to this row and that column. Negative 1 out of 5 times 7 would be negative 7 out of 5. Yes, just move like this and that. You have negative 7 out of 5. And then what about this? 2 out of 5 times 5. That gives you 2. Now you can use your calculator here. This is like 3 out of 1. So the LCM would be 5. So this would be 28 minus 15 out of 5. Because this over 1 here, so the LCM is 5. So 5 goes into itself once. 1 times 28 will be 28. 1 goes into 5 times. 5 times that will be 15. What about this one? This will be 5 negative 7 plus 10. And again here the LCM is 5, but this is 2 over 1. So I ask myself, 5 goes into 7 many times? Goes into itself once. So 1 times this negative 5, negative 7, will give us negative 7. And then 1 will go into 5 times. 5 times this 2, it will be 10. So what is the final answer? 15 from this is 13 out of 5. And negative 7 plus 10 will be 3 out of 5. So that is the answer. That is the answer we used the matrix method. We used the matrix method. You may have wanted to use elimination or substitution, which you're already aware of. Let's see what we will have gotten if we were to use that elimination. Let's see if we would get the same thing. If we were to use elimination, so I only need to divide this equation by 2. So if I divide this equation by 2, I would have A plus 3 out of 2B, and then this would be 7 out of 2. And this equation is A plus 4B is equals to 5. So I would subtract these equations. And look at this. This is just 3 out of 2 minus 4 out of 1. So there is 2. There is 2. And what we have there is 3 minus 8. 3 minus 8, which should be negative 5. B out of 2. And this would be equal to, this is 7 out of 2. And this is 5 out of 1. So then the lesson there again is 2. And this would be 7 minus 10, which would be negative 3 out of 2. So what is B? Multiply both sides by this. It will be negative 3 out of 2 times negative 2 out of 5. And this gives you 3 out of 5. That gives you 3 out of 5 as B. Now just go back to one of the equations, either this, and substitute B to find A. So when you do that, you will have that A is 5 minus 4B, but B is 3 out of 5. So the LCM is 5. So that means I will have 25 minus 12 out of 5, which is 13 out of 5. And let's go back to the question. I was just showing you that this other method that elimination or substitution would still work. but I wanted to use matrix method because that is a question. The question is told us to find using matrix method, and so we used matrix method. And the first thing that we did was find the determinant of the matrix. Oh no! First of all, we extracted the coefficients of A and B from the matrix, and then found the determinant of their matrix. Then found the inverse of their matrix. Then to find AB, we multiply by the inverse on this side with the constant, and we found that A will be this. So the question is, what is the solution for? What is the solution for this? So the solution, this has only one solution. Actually, it doesn't need you to find A and B. The question is not find the value of A and B. This is not the question. The question does not ask us to find the value of A and B. The question asks us to solve this. So this has only one solution. And the solution to this is just 13 out of 5. And then 3 out of 5. It's a vector in vector form. So this is the solution to this system. It's not about the value of A and the value of B. That is not the question. Now, you can solve so many of these type of equations by matrix method because it's something you've done before. I'd be interested on how to solve if you're given 3 unknowns and 3 questions. You're given 3 unknowns and 3 questions. That one I'd be interested on how to solve that. And there's so many methods of solving that. So that is what I'll be looking at later. I want to teach you how to find determinants of higher order matrices. That means at the end of this lesson, we should be able to find determinant of a 3 by 3 matrix, determinant of a 4 by 4 matrix, determinant of a 5 by 5 matrix. I want to begin with a very simple example. Find that A, if A is 2, 1, 3, 4, 1, 6, 1, 0, 2. Find the determinant of this matrix. And there are so many ways of finding the determinant of matrix. If it's a 3 by 3 matrix the way it is, if it's a 3 by 3 matrix, it will be easier to just take the matrix as given, take the matrix as given. I'm showing the easiest way to find the determinant of a 3 by 3 matrix. And then take these 2 rows, these 2 columns, add them here. I've added the first column, then add the second column. I've added the second column. So the question was to find the determinant of this matrix. Identify the 3 diagonals. This is a diagonal. There's this other diagonal. And there's this other diagonal. So identify 3 diagonals running from, just a minute, let me just write properly. 3 diagonals running from top left to bottom right. and multiply along these diagonals as you add the results. So you identify 3 diagonals running from top left to bottom right and multiply along these diagonals as you add the results. If that's okay, you've written that. So that's what I want to do. I hope you're writing notes. So don't erase those notes that I've erased. Just want to create space to do the question. But that is part of what you need as your notes. So I've identified these diagonals. I want to multiply along this diagonal. This 2 times 1 times 2, that gives us 4. 1 times 6 times 1, that is 6. I said you multiply and add the result. And then 3 times 4 is 12 times 0 is 0. This gives us 10. Identify this other diagonal. This time, the diagonal is running from, let me see if I can change the color here. The diagonal is running from top right to bottom left. So I want this diagonal. I want this diagonal. And this other diagonal. So what I'm saying is identify 3 diagonals running from top right to bottom left. Multiply along these diagonals, multiply the result along these diagonals, multiply and add the result. Multiply and add the result. So we identify, multiply this and add the result. Subtract the second result from the first result. Subtract the second result from the first result. What I mean is, I would have minus, multiply this, I get 8. Multiply this, get 0. And multiply this to get 3. So the earlier result was 10. And the new result here is 11. So the determinant of this matrix is negative 1. The determinant of this matrix is negative 1. So we just identified 3 diagonals. We multiply along these 3 diagonals, added the result here, we got 10. Then this gave us 8, this gave us 0, this gave us 3. So that is 11. Subtracted this second result from this first result, and we found the determinant is 11. Now, this method can only be used if the matrix is a 3 by 3 matrix. If a matrix is of higher order than a 3 by 3 matrix, this method will not work. So let me now show you a method that will work for any size of matrix. And we want to see if we will still get negative 1. So I want to do the same question using now the method that I expect you to know, and that this method that I want to show you now can apply for any size of a matrix. Now, so this method I want to show you, we are calculating the determinant along a row or along a column. So identify a row and find the determinant along that row. For instance, I want to do my determinant along the first row. So I come to this position of 2 here. I write that 2. And then, if I was to delete the row of 2 and the column of 2, if I was to delete the row of 2 and the column of 2, what matrix remains? The matrix that remains is 1, 6, 0, 2. So I'm already finding the determinant. So I've taken these 2, I've multiplied by the determinant. Just a minute. I want this one to be a vertical line. Vertical line means a determinant. That if I write but 1, 6, 0, 2 inside the vertical lines, it means find the determinant of this matrix. Now, so I've written, I said I wanted to find my, just a minute, there was a 2 and a 3 there, let me just return them. There was a 2 and a 3 there, before we forget. There was a 2 here and a 3 there, before we forget. Good. So then we said that for us to find the determinant, we take, I want to do it along this row. And I said you can choose any row, you can even choose this row and do it along that. You can choose this row and do along this. You can choose this column and do along this. You can choose this column and so on. So you just choose what you want and do along that. So I've chosen this row, and the first element in this row is 2. So I multiply 2 times the determinant of the matrix that remains when you delete the row of 2 and the column of 2. When you delete the row of 2 and the column of 2, the matrix that remains is 1, 6, 0, 2. Then minus 1, that is the second element. Minus 1. I'll tell you where the minus is coming from. Minus 1, delete the row of 1. So this is 1. So its row is this, and its column is this. When you delete the row of 1 and the column of 1, the matrix that remains is 4, 1 and 6, 2. Then plus 3. I'll tell you where that plus is coming from. When I did this 3, now delete the row of 3 and the column of 3. When you delete the row of 3 and the column of 3, the matrix that remains is 4, 1, 1, 0. 4, 1, 1, 0. Now find this determinant is 2 minus 0. 2 minus 0, so which is 2. Then minus 1 into this determinant is 8 minus 6. 8 minus 6, which is 2. Then plus 3. This determinant is 0 minus 1. 0 minus 1, which is minus 1. Now, when you do this, you'll find this to be 4, and you'll find this to be negative 2, and you'll find this to be negative 3, and the whole thing is negative 1. So that is the determinant of this matrix. That's the determinant of this matrix. So I already said I'll tell you where this negative is coming from, and where this positive is coming from, and where this positive is coming from. So the sign of Rij, the sign of R, where R is the element, for example, 2, the sign before this would be given by R raised to, no, just a minute. The sign would be given by negative 1 raised to I plus j, where I is the row of this and j is the column of this. So for instance, this element 2 is in row 1, column 1. So the sign will be -1 raised to row 1, column 1. So it's -1 raised to 2. So you know that -1 raised to 2 will be +1. And that's why you see positive at this point. What about at this point? This one is in row 1, column 2. So the sign will be row 1, column 2. So it is -1 raised to 3. Negative raised to an odd number, the answer is negative. And that's why you see negative here. What about here? I have the element 3 in that position, which is in row 1, column 3. So this is, just a minute. So the sign will be -1 raised to row 1, column 3, which is -1 raised to an even number. So -1 raised to an even number, the answer is positive. And you saw it here, the answer was positive. So the answer is positive even for this. Now, so that means this sign should be alternating. It will be positive, negative, positive. So this was positive, so this one will be negative, positive. So if this is negative, then this will be positive, negative. So you can see this is negative, so what follows here is positive. So let me see, positive, negative, positive, negative, positive, negative, positive, negative, positive. That is how the signs will be alternating. Now, so we found the determinant of this matrix along the first row. And as I said, you can do it along the second, the third, and so on. Or you can even do it along the columns. Let's now try and do it along columns. I want to choose any column. Let me choose column 1. No, column 2. Let me choose column 2. Let me choose column 2. I want to do it along column 2. And I've discovered column 2 has a 0. So a column that has a 0 or a row that has a 0 is easier to get determined along such a column or along such a row because zeros would make the work easier. Because you know that 0 times anything, the answer will be 0. So that is why I've chosen on this column. Now, this column, this element is 1. So delete the row of 1 and the column of 1. Delete the row of 1 and the column of 1. The matrix that remains is 4, 1, 6, 2. 4, 1, 6, 2. Now, just a minute. The sign is negative. Because it's supposed to be positive, negative. The sign is negative. So if this is negative, then this is positive. You can just try negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. So that's how signs of alternating. I say they're alternating. So the sign here is negative. So -1 times the determinant of the matrix that remains when you delete the row of 1 and the column of 1. The second element in this column is 1, and the sign is positive. So delete the row of 1 and delete the column of 1. When you delete this row, middle row, and this middle column, what is left is 2, 3, and 1, 2. Now what follows is this element is 0. But now It will be negative 0 multiplied by anything here. This thing will be 0. Let me just delete the row of 0 and the column. The row of 0 and the column of 0. We are left with 2, 3, 4, 6. That's why I said it is easier to do it along a row or along a column that has zeros, because that makes your work easier. Now, what does the first one there give us? Negative 1 into, this is 8 minus 6, which is 2. 8 minus 6. Then plus 1 into, this is 4 minus 3. 4 minus 3, which is 1. So do you have? Negative 2 plus 1, which is negative 1. So you found the same determinant. And I said you can do determinant along any row or along any column, so long as you remember the steps. Let us find the determinant of a 4 by 4 matrix. And that will be our last example. And then next time when we meet, next video, I'll begin by showing you how to find inverses of higher order matrices. Because you need to know how to find inverses of higher order matrices. But I've already shown you how to find the determinants. Let me see. 1, 2, 3, 4, 0, 1, 7, 3, 3, 1, 2, 1, 1, 1, 2, 2. Yes, here's a matrix. The question is find the determinant of this matrix. I will choose the first column because it has zeros. It has a 0, so it becomes very easy for me. And I can even create another 0 if I want to make it easier. I can create another 0. If I subtract this row from this row, I can create a 0 in this position, and that makes my work even easier. But let me just leave it the way it is. I've noted that it has a 0, and I want to do it along that. What will be the signs? What will be the signs? So the signs will be positive. Let me just use another pen. The sign there will be positive, negative, positive, negative. I'm doing along the first row. So remember, I must reduce this to 3 by 3 matrix, and then reduce the 3 by 3 matrix to a 4 by 4 matrix. No, to a 2 by 2 matrix. Let me see. I'll have a determinant there. I'll have this will be a bit long because the 4 by 4 matrix, you must reduce it to a 3 by 3 matrix first. So I would have 1 into and the column of 1. When you delete the row of 1, the column of 1, what you have is 1, 7, 3, 1, 2, 1, and 1, 2, 2. So this is the one I'm saying we'll have to reduce it to a 2 by 2. So it means this thing will be long, a bit, a long thing. Now come to this. This is multiplied by 0, so let's just skip that because it will just give us 0. In fact, what I should have done to make my work easier, I should just have created a 0 at this point and create a 0 at this point to make my work easier. Since I already have a 0, let me create a 0 here and create a 0. It's very easy. But still you can do it the way I'm doing it, get it some other, but it will be long. The long thing. So I want to make it easier. So to make it easier, let me create a 0 here. How do I create a 0 here? Take row 3 minus 3 multiplied by row 1. How do I create a 0 here? It's in row 4, just subtract row 1. So that my new matrix will be the new matrix I want to use. Therefore, I want to use this because this will take a very long period of time. Row 1 remains where it is as 1, 2, 3, 4. Row 2 already has a 0 here, so I just leave it as 0, 1, 7, 3. But I want a 0 here, so I've said take this row 3 minus 3 multiplied by row 1. So 3 minus 3 multiplied by this 1 equals 0. And this is 1 minus 3 multiplied by 2. 3 multiplied by 3 is 6. When I subtract, I have negative 5. What about this? 2 minus 3 multiplied by 3. 3 multiplied by 3 is 9. So when I subtract, I have negative 7. 1 over 0. Do it for the entire row. 1 minus 1. So 1 minus 2 will be negative 1. 2 minus 3 will be negative 1. And 2 minus 4 will be negative 2. So I now have zeros. This will make my work easier. When you create zeros along a row or along a column and get determinant along that row or along that column, your work becomes great. So that means I should not proceed with what I was doing because this one will have taken a very long time. I should not proceed with that. The only thing I just need to know is to confirm whether my subtractions here were correct. This remains where it is. I was taking 3 minus 3 here. So I'm going to this the entire row by 3 and subtract from this one. So 3 minus 3 is 0. 1 minus 6 is negative 5. 2 minus 9 is negative 7. 1 minus 12 is negative 3. So I've confirmed the third row that it will just remain where it is. And then I also took this row minus that row. 1 minus 1 is 0. 1 minus 2 is negative 1. 2 minus 3 is negative 1. And 2 minus 4 is negative. Now I want to get along this. So therefore, the determinant will be 1 is 1 multiplied by the determinant of the matrix that remains when you delete this row and this column. When you delete this row and this column, the matrix that remains is 1, 7, 3, negative 5, negative 7, negative 11, negative 1, negative 1, negative 2. This is the determinant of this matrix. But now we have also to reduce this. These are 3 by 3. So let's again do it along this one. I don't need to reduce zeros. Let's just do it. So this will be 1 into. I want to do it along this first row, this first column. So it will be this 1 times the determinant of the matrix that remains when you delete row 1 and column 1. When you delete row 1 and column 1, what you have is negative 7, negative 11, negative 1, negative 2. I'm doing it along this column. So this is plus, minus, plus. Plus, minus, plus. That will be the sign. Plus, minus, plus. So the minus there of the sign, then this minus will give us positive. Now, this is 5. Delete the row 5 and the column of 5. What you are left with is 7, 3. Negative 1, negative 2. So this was plus, minus, plus. So that plus and this minus gives us minus. Delete the row of negative 1 and the column of negative 1. And what you have is 7, 3 and negative 7, 11. Delete this and that. 7, 3, negative 7, negative 11. So what is your answer here? The answer is the one that is outside here, multiplied by, this will be positive 14. Positive 14 minus 11 will give us that. Positive 14 minus 11 will give us that. Plus 5 multiplied by, this will be negative 14. Negative 14 plus 3 will be negative 11. We now to get determinants, so it's very easy here. This product minus this product. This product is negative 14. This product is negative 3. So when we subtract negative 3, that is why negative 3 from, when you subtract negative 3 from negative 14, this becomes positive. That's why I've written negative 14 plus 3 and again negative 11. So we are done with that. Let's now come to this other part. Negative 1, remember this bracket is a 1 here. Negative 1 multiplied by, this is negative 7, 7. Negative 7, 7 plus 21. Negative 7, 7 plus 21. That gives you negative 56. That gives you negative 56. So what is the answer? Inside the bracket, I have 3. So you can see, I first of all introduced zeros and made it easier for me to find the determinant. Otherwise, if you would not have introduced zeros, the work would have been a bit long for you to get the determinant of these functions. And of course, you can do it. You just take this one, multiply by the determinant that is left. When you delete the row of 1 and the column of 1, and this is that matrix, and then minus 0, multiply by the determinant that is left when you delete the row of 0 and the column of 0, and then times, no plus, no negative 3, multiply by the determinant that is left when you delete the row of 3 and the column of 3. And you can see that the 3 by 3 matrix. Then this was plus, minus, plus. Then now minus 1. Delete the row of 1 and the column of 1, and the matrix that is left is this. So you've reduced it to a 3 by 3 matrix everywhere. Now go back and reduce it 2 by 2. Every bit of it, reduce it to 2 by 2, and see what you get. You'll find the same answer. Try as many examples as possible. That's how we find the determinant of higher order matrices. You can use this method again to get determinant of 5 by 5 matrix, 6 by 5 6 matrix, and so on. Now, if you're not subscribed to my YouTube channel, remember to subscribe so that whenever I upload any other lesson, you can easily see it.